In chapter 4, we talked about how to factor quadratics. And today what we're going to do is we're going to be factoring polynomials. So we're going to do some factoring that you probably haven't seen before, but it's going to require you to use all of your old factoring as well. And so we're also going to talk about how to look at a polynomial equation, and even though it may not look like it's a quadratic, there may be a way to get it into quadratic form. So the sum and difference of cubes, this is a type of factoring that you haven't seen yet. Now what I want to remind you of is that when you have the difference of perfect squares, this should be one of the types of factoring that you are most comfortable with, because you've seen this now for 3 years. If you have x squared minus 25, that can factor to x minus 5 times x plus 5. Now what you need to recognize, and some of you are not recognizing this, is that when you have a sum of perfect squares, this won't factor. A lot of people on the test wrote that this was x minus 5 times x plus 5. But if you look at the last times last in this case, you end up with a negative 25. You cannot factor a sum of perfect squares. However, when it comes to perfect cubes, you can factor the sum or the difference of perfect cubes. And this gives you the general form of how you do that, and I'm going to show you a couple of examples. There's a way to remember how you do this. If we're looking at a cubed plus b cubed, so we have a sum of perfect cubes. I want you to write above each one what the cube root is. So we have a times a times a, so it looks like a little flower or a little firework. And here we have b times b times b. Now when you factor this, you're going to double bubble, but this time you're going to put a smaller bubble for a binomial and a bigger bubble for a trinomial. Now the signs that we're going to put in these are going to be same, opposite, always, positive. So same sign, opposite sign, and then always positive. So the same sign would be plus, so we're going to put a plus here. Then the next sign is going to be opposite, so we're going to put an opposite here. And then this one, the third one, is always positive. We're going to take one of these first cube roots and put it here. So that's going to be a. We're going to take one of these and put it here. We're going to take the other two, so a times a is a squared, and we're going to take the other two and put them over here. Now this middle term is just one of the first cube roots times one of the second cube roots. Oops. So you always have to ask yourself, do I have a perfect cube? And how do you know if you have a perfect cube? If I have x to the third, that's a perfect cube because it's x times x times x. If I have x to the fourth, there's no good way that I can write that as a perfect cube, so that's not one. If I have x to the fifth, same thing. We can't write that as a perfect cube, but if I have x to the sixth, well, that's going to be x squared times x squared times x squared. X to the seventh, can't happen. X to the eighth, even though you think it should be able to happen because 8 is a perfect cube, it can't. X to the ninth can now be written as x to the third times x to the third times x to the third. So just looking at the exponent alone, in order to have a cube, a perfect cube, that exponent is going to have to be a multiple of 3. So looking at this, in order to recognize if this can be factored, because if you only have two terms and I'm asking you to factor it, you can look and say, is it a difference of perfect squares, which this is not because x cubed is not a perfect square. Is it a difference of perfect cubes? Well, you put the cube root of 400 into your calculator, and just to give you an idea of how to do that, if you hit second math, oops, I did that wrong. Let me quit. So hit second math. Something is wrong right now. Oh, no wonder you don't hit second. You just hit math. And you look down and you see the cube root right there at number 4. So hit 4 and put 400 in. Now if you get a beautifully wonderful integer, then that's a cube root. If you don't, It's not a perfect cube. So this cannot be factored. Not factorable, meaning that it's relatively, these two numbers are relatively prime to each other. Now, if we look at this next one, always the first step of factoring is to pull out your greatest common factor. So I look at 24 and I look at 3, and I know they have 3 in common. And I see that in each of these monomials that there are x's, so I can pull out an x squared. So this is going to become 3x squared times 8x to the third plus y to the third. Now, I actually wish I had made this a subtraction problem in your notes, so I'm going to actually do that right now. So I want everybody to change this to a subtraction problem, because we just did a sum of perfect cubes, so we're going to make this a subtraction problem. So be sure you don't lose your greatest common factor. Always write that there. But then ask yourself, do you have a perfect cube? And yes, you do, because 8x cubed can factor to be 2x times, 2x times 2x, and y cubed can factor to y times y times y. So we're going to do our double bubble now. Remember, make one small for a binomial, make one big for a trinomial, and put in your signs. So we have same, in this case same is negative, opposite is positive, and then always positive. You have your signs in place. Take one of these perfect cube roots and put it there. Take one from the other side and put it here. And then take the other two, multiply them together. That's going to be your first term of the trinomial. And the other two are going to be the last term here. Now this middle term, you're just taking one of these times one of these. So that's going to be plus 2xy. And now that is fully factored. So factoring techniques that you've learned, we've already used some of these today. The greatest common factor, that's always going to be the first thing that you check for. Then you look and see how many terms you have. And if you have 2 terms left after you've pulled out the greatest common factor, you're going to do one of 3 things if it's factorable. You're going to look and see if it's a difference of 2 squares. You're going to look and see if it's a sum of 2 cubes, and you're going to look and see if it's a difference of 2 cubes. If it's one of those 3 things, then you can factor it further, and we've seen that today. Perfect square trinomials. If you think about number 9 from your test, a lot of you didn't recognize a perfect square trinomial. You had 9x squared plus 12x plus 4 on your test, and I had it set equal to number 6, and it said solve using the square root theorem. So you should always look and say, my first term, is it a perfect square? Yes, it is. My last term, is it a perfect square? Yes, it is. And when you write down those square roots, say, well, if I multiply those together, so I take 3x times 2, that's 6. If I multiply that times 2, do I get my middle term? And yes, I do. So this is where you can factor it to 3x plus 2 quantity squared. And if we had had 9x squared minus 12x plus 4, then that's going to factor to 3x minus 2 quantity squared. So always look for those perfect square trinomials, because people tend to miss those. And certainly you can treat it like a regular trinomial, and you can do that effectively, but it's easier to just recognize it. General trinomials are what you want to do. A lot of you tic-tac-toe for the general trinomials. The book teaches how to do it this way that's listed right here. General trinomials are what people struggle with the most in factoring, and if you're not able to do that, you need to come in and get some help, because by now you should be able to factor general trinomials. Factoring by grouping, anytime you see that you have 4 terms, you're going to look at factoring by grouping. And that's when you put the first 2 terms together. Hopefully they're in an order that allows you to do this. Factor out your greatest common factor from those, factor out your greatest common factor from the last 2 terms, and see if you have a binomial that matches, that you can then pull out and get it into factored form. So applying this, factor this polynomial. So we're going to look at the first two terms and the last two terms. So I can pull x squared out of our first two terms, and I get x squared times x plus 5. I can pull out a negative 2 from our last two terms, and I get x plus 5. And that's good, because we have a matching binomial. So I'm going to pull out x plus 5 from this term, and when I do that, I'm left with x squared. When I pull it out of this term, I'm left with minus 2. Now you always want to check right now and say, can I factor this anymore? Because you have this binomial here that has a squared term. So you say, okay, I have two terms here. One's a squared term. Is it a difference of perfect cubes, a difference of perfect squares, or a sum of perfect cubes? And none of those work. So this is now factored fully. The only one I care about on this page is problem B, and so we need to look at 64x to the 6th minus y to the 6th. And are they perfect cubes? Yes. 64 is 4x squared times 4x squared times 4x squared. Y to the 6th is going to be y squared times y squared times y squared. So now we're going to do our double bubble for a binomial and a trinomial, and our signs are going to be same, opposite, always positive. So take one of these and put it here. Take one of these and put it here. And now we're going to take both of these and multiply them together. So we get 16x to the 4th. And we're going to multiply both of these. So this is going to become y to the 4th. And then our middle term is just going to be 4x squared y squared. Now this is a great example of one where we now have a difference of perfect squares. So this we can break down. This is going to become 2x minus y times 2x plus y. And this term is going to stay exactly like it is. So factor, these are just check your progress. All right, determine the dimensions of the cubes below. If the length of the smaller cube is 1/2 the length of the larger cube, and the volume of the shaded figure is 23,625. So the larger cube volume, each side of the larger cube is 2x, so we want to take length times width times height, and that gives us 8x cubed. The smaller cube volume, each side is x, so we're going to say x times x times x equals x cubed. Now we want to take the volume of the larger cube and subtract from it the smaller cube, because that's what's going to be left, and that's what is equal to 23,625. This becomes 7x cubed equals 23,625. Divide by 7, and we get 3,375. So when you take the cube root of that, you get x equals 15. So the large cube is 30 by 30 by 30, and the small cube is 15 by 15 by 15, because it asks for the dimensions of the cubes. Okay, key concept is recognizing that something is in quadratic form. Everything we've done until now always had ax squared plus bx plus c. And we were only dealing with x squareds and then the linear power of x. But there is a way that you can get something in quadratic form by doing what's called U substitution. So in this case, the way you know if something can be put into quadratic form is you're going to look at the middle term. In this case, the variable part of the middle term is x cubed. Just looking at the variable part of that, if you square that, you get x to the sixth. If that matches the first term, the a term of your quadratic, then you're going to be able to form a quadratic equation out of this. So what we would say in this case is that u equals x cubed. So when we go and substitute that into this expression, we're going to have 2u squared minus u plus 9, because u squared is going to equal x to the sixth. Can this one be put into quadratic form? Well, our middle variable term is x cubed. If we square that, we get x to the sixth. That variable term does not match what's in the first term, so this cannot be put into quadratic form. So let's do one more of those. So here we have 6x to the 10th minus 2x to the 5th minus 3. So look at the variable portion of that middle term, which is x to the 5th. If we square that, do we get the variable portion of that lead term? And we do. So this one is going to be able to be put into quadratic form. We would say that u equals x to the 5th. And if u equals x to the 5th, then u squared is going to equal x to the 10th. So we'd say this is 6u squared minus 2u minus 3. Down here, our middle variable portion is x to the 3rd. If we square that, we get x to the 6th. That does not match the variable portion of our lead term, so this cannot be put into quadratic form. So now let's use that to solve this equation. Let's determine if it can be put in quadratic form. So the variable portion of our middle term is x squared. If we square that, we get x to the 4th. And that is indeed the variable portion of our first term. So we're going to say that u equals x squared, and therefore u squared equals x to the 4th. So when I go and substitute u into this equation, we get u squared minus 29u plus 100 equals 0. Now we're going to factor that. So we get u minus 25. Ooh, computer's going crazy. U minus 25 times u minus 4 equals 0. So we would get that u equals 25 and u equals 4. Now we're not done. Don't think you're done yet. You have to go back and say, but u is equal to x squared. So we're going to say x squared equals 25 and x squared equals 4. Now here's the next mistake you're going to make. You have to square root both sides of this. When you square root something, you have to include plus or minus. So we get x can be plus or minus 5. And going over here to this one, we take the square root, we get x can be plus or minus 2. So this particular equation can be put into quadratic form, and it has 4 solutions. X can be plus or minus 5, and x can be plus or minus 2.